the topic hydrodynamics of gas, liquid, solid, three-phase fluidized bed. So a three-phase fluidized bed consists of three phases. One is gas phase, second is the liquid phase, and third is the solid phase. Usually in the fluidized bed, as you know, a bed of solid particles comes to a state of suspension by the flow of the fluid. The fluid may be gas, liquid, or it may be together gas and liquid. When it is two fluids are there, gas and liquid, then the fluidized bed is gas, liquid, solid fluidized bed. The outline of my presentation is introduction, classification of gas, liquid, solid reactors. Although my main discussion will be on gas, liquid, solid fluidized bed, but what are different types of gas, liquid, solid reactors, that also we will discuss. Then modes of operation of the gas, liquid, solid fluidized bed, the flow regimes, experimental hydrodynamic study, and computational hydrodynamic study. Gas, liquid, fluidized beds are the most promising device for three-phase operations because of the intimate contact of the three fluid phases, gas, liquid, and solid. Many types of operations are carried out in this gas, liquid, solid fluidized bed. Because of vigorous mixing in this reactor is possible. So gas, liquid mass transfer, liquid, solid mass transfer, or it is gas, solid mass transfer, depending upon the type of fluidized bed, are possible in this gas, liquid, solid fluidized beds. And this gas, liquid, solid fluidized bed is widely used in chemical, petrochemical, and biochemical processing. Few of the examples are in the hydrotreating and conversion of heavy petroleum and synthetic crude, H-oil process, that is hydrogenation and hydro desulfurization of residual oil, in hydrocarbon cracking and reforming, oxidation of naphthalene to phthalic anhydride, that is a catalytic one, fluid catalytic cracking, as you know, FCC, which is common in petroleum industries, that is a catalytic type. Then another one, non-catalytic operations also, this gas, liquid, solid fluidized bed is used, that is coking of petroleum residues. Then H-coal process for coal liquefaction as a turbulent contact observer for flue gas desulfurization. It is used in many pharmaceuticals and mineral industries like penicillin production, etc. Then some physical operations and in biochemical processes such as fermentation, aerobic and anaerobic wastewater treatment. The classification of gas, liquid, solid reactors. 2A, it is classified. One is the factors and the variations. So state of motion of solid particles, because three phases are present, gas, liquid, and solid, and solid is the first and foremost thing for the fluidized bed, because as per the definition of the fluidization, a bed of solid particles comes to a state of suspension by the upflow of either gas or liquid or solid. Gas or liquid, or the combination of gas and liquid. So the solid is having the importance. So state of motion of solid particles, either it is stationary or it is slurry suspension with mechanical agitation, slurry suspension without mechanical agitation, and fluidization. Then the types of operation, the liquid phase or the gas phase. So gas continuous, either it is, or liquid is either batch or continuous, solid is batch or continuous. relative flow direction of phases for continuous operation, gas and liquid, co-current upflow or co-current downflow, then counter current flow or cross current flow. Solid may be flowing in upward or a downward direction. The situation of phases: the gas is the continuous phase or discrete bubble form, gas might be moving in the bed. Liquid is continuous phase or in the form of film or in the form of droplets. Solid, either it is packed, slurry suspension, fluidization with either liquid or gas as a continuous phase. The classification of gas liquid solid reactors and the contactors based on the previous overall classification. One is the operation one, that is class 1, that is the packed bed. The type of reactor is the packed bed reactor. The operation for gas and liquid, then the continuous phase, operation for solid, particle size, force of solid suspension, gas liquid mass transfer, wall to bed heat transfer, fluid mixing, and the process application. These are the classifications for the packed bed reactor. So column 1, as you see, it is the counter current, or concurrent upflow, concurrent downflow. Where the continuous phase, when the continuous phase is the gas, there is trickle flow, that means water or the liquid trickles down. And when the continuous phase is the liquid, the gas moves in the form of bubbles, dispersed bubble flow, or it is slug flow. Then operation of solid is batch in packed bed. Once it is there in the bed, always it remains intact in the bed. The particle size normally used in the packed bed of size greater than 1 millimeter. The force of solid suspension is stationary. Gas liquid mass transfer, gas liquid phase controlling here, and the KLA, that is the mass transfer coefficient, liquid based on the liquid phase, that is 5 into 10 to the power minus 4 to 0.1 liter per second for the counter current operation, and for concurrent again it is up to 1 liter per second. Then wall bed heat transfer, poor for trickle flow and fair for dispersed bubble flow or slug flow. Fluid mixing is the low fluid mixing is there in the packed bed. Process application: absorption, desorption, chemical absorption, gas liquid solid catalytic reaction, biochemical reaction. Then another type reactor in the class 1 is the packed bubble column, where the operation of gas and liquid is the counter current, concurrent upflow, internal liquid circulation. These are the classifications. And in the packed bubble column, continuous phase is the liquid, the operation is batch as far as the solid is concerned, and the particle size used is more than 10 millimeter. That means high Faraday packing is there in the case of a bubble column. The force for solid suspension, there is no suspension, solid is stationary. Liquid phase controlling here, KLA value 0.04 to 0.2, and wall to bed heat transfer is fair. Fluid mixing is the intermediate. Applications are chemical absorption, biochemical reactions, etc. Then operation class 2, the reactor type is the agitated vessel. Operation for gas and liquid is the cross current in agitated vessel. Continuous phase is the liquid. Operation for the solid is either it is batch or continuous. Particle size normally small particle size less than 0.1 millimeter. Force of solid suspension is mechanical agitation by the use of terror or such kind of device. Gas liquid mass transfer, liquid phase controlling, and low it is very low value to up to 0.8 it is, that is from 0.005 to 0.8. Wall to bed heat transfer is good. Fluid mixing is complete mixing of the fluid is there. Gas liquid solid catalytic reaction, biochemical reaction, these are the process applications. Operation class 3, gas sparge slurry reactor. The operation for gas and liquid phases, co-current, counter-current, internal liquid circulation, external liquid circulation, and jet mixing. Here again, the continuous phase is the liquid. Operation for solid is continuous. Continuous flow of solid is there in this reactor. Particle size less than 0.2 millimeter. Force for solid suspension, mainly the gas. Gas actually impart the drag on the solid particles. Gas liquid mass transfer, liquid phase controlling, KLA value 0.005 to 0.3. Wall to bed heat transfer is good. Fluid mixing is very high. Process application, gas liquid solid catalytic reaction, chemical absorption, biochemical reaction, absorption, adsorption, processing. Then operation class 4, the type of reactor is fluidized bed, spouted bed. Operation for gas and liquid, co-current upflow, counter current. The continuous phase is liquid, gas. Okay, either liquid is continuous or gas is continuous. Operation for solid, it can be batch or it can be continuous. Particle size for co-current, particle size normally 0.2 to 8 millimeter. Liquid continuous, that is the turbulent contact observer, and a particle size 3 to 40 millimeter. Where the density of the solids, these are low density solid particles are used, 90 to 1200 kg per cubic meter. For gas continuous, that is turbulent contact observer is used. Force for solid suspension, liquid and gas, liquid continuous, mainly gas for gas continuous. So force of solid suspension, either it is the liquid or it is the gas, depending upon the flow rate of liquid or the gas. Gas liquid mass transfer, liquid phase controlling, the value 0.005 to 0.2. Wall to bed heat transfer, very good for the liquid continuous system. Fluid mixing, intermediate for fluidized bed, complete mixing for shallow spouted bed. Process applications, fluidized bed co-current system, gas liquid solid catalytic reaction, biochemical reaction, chemical absorption, counter current systems, biochemical reaction, turbulent contact observer, physical absorption, chemical absorption, particulate collection, cooling tower, and the spouted bed, it is co-current for the purpose of dissolution, gas liquid solid reaction, drying, granulation, and counter current systems similar to that of the turbulent contact observer. This is used. So these are the classification of different types of reactors. Then the mode of operation, although there are considerable similarities between the gas phase slurry column and a gas liquid solid fluidized bed, as we have seen, but there is distinct difference in operation exists between these two systems, spaced slurry column and the fluidized bed. As you see in the schematic here, the top one is this one is the slurry column and the bottom one is a fluidized bed. So the difference is based on the particle size, volumetric fraction of solids, cause of suspension of the particles. The bed expansion may be uniform, non-uniform in fluidized bed. The bubbles intensify the mixing of solid particles in fluidized bed. The solid particles in both systems can be operated in either a batch or a continuous mode. In slurry column, the solid particles are usually carried in and out by the liquid stream. As you see here, okay, the solid particles are entering to the system with the liquid, that is in the form of slurry. Then after processing it is leaving. But in fluidized bed, the solid particles may be the batch ones. Solid is not getting out from the system, or solid may get out from the system. Also, externally we can charge the solids here. The solids we may charge in case of the fluidized bed. So in fluidized bed, the solid particles are supplied or withdrawn independent of the liquid stream, whereas in slurry column, it is in the liquid suspension, the solid particles enter into the vessel. According to the relative direction of the gas and the liquid flow, the modes of operation is divided into two types, co-current and counter-current. So, as my topic is the three-phase fluidization, gas, liquid, solid fluidization. So, next we will see the classification of this gas, liquid, solid fluidization. Based on the modes of operation, it is co-current or counter-current, and based on the contacting pattern between the particles and the surrounding liquid and gas, the classifications are like this. This is the taxonomy which was given by Epstein in his publication in 1981. The three-phase fluidization, either it is co-current or it is counter-current. Again, the co-current, it is bubble flow or trickle flow. Bubble flow means liquid is continuous and gas moves in the form of bubbles, and in trickle flow, your gas is continuous and liquid trickles down. That means just moves on the surface of the solids in the form of film. That is trickle flow. Again, bubble flow is classified into liquid supported solids or bubble supported solids. When the bubble size is very small, that means in the discrete bubble flow phase, the liquid supported solids are there, but in the coolest bubble flow regime or slug flow regime, bubble supported solids are there. That means the gas bubbles impart force to the solids to make it suspended. And in counter current, again it is classified as a trickle flow, which is a turbulent bed conductor, and the bubble flow. Again, bubble flow means it is the liquid continuous, and in trickle flow, gas continuous, liquid trickles down. Again, bubble flow in counter current classified as bubble supported solids and liquid supported solids. If it is liquid supported solids and counter flow operation is there, downward flow of the liquid, inverse three-phase fluidization we get, where low density solid particles are used. And if liquid is stationary, in between we have liquid stationary liquid, then only gas is moving. Then the gas bubbles will support the solid particles, so bubble supported solids we are getting in between. The mode 1A of the operation, it is the co-current fluidization with liquid as the continuous phase. As you see here, this is the mode 1A, liquid is the continuous. So both in the co-current flow in the upward direction, liquid and gas moving, and solid particles are there. Solid particles are in suspension, and the red color, the bubbles you see, these are the gas bubbles, and the liquid is the continuous phase. Mode 1B, co-current fluidization with gas as the continuous phase. Here you see the gas is the continuous phase, entire space is occupied by the gas, and solid particles are there, which is the green dots as you see, and there are few curved lines, small curved lines as you see, that way represents the flow of the liquid in the form of just films of fluid flowing over the solids. That means liquid trickles down. Then mode 2A, it is liquid in the downward flow and gas in the upward direction, that is the counter flow operation. Inverse three-phase fluidization, the bed of solid particles are fluidized by downward liquid flow opposite to the net buoyant force on the particles. So here the particles are lighter than that of the liquid usually. So if the bed is occupied with the liquid and the solid particles are present, so the solid particles will float, and it will be attached to the top distributor. This is the distributor, top distributor plate. So it is in the floating condition. There is no fluidization. That means it is forming a fixed bed at the top. So when the liquid flow is there in the downward direction, because of the drag that the liquid imparts on the solid particles, those they are floating at the top of the liquid, then the solid particles are dragged down, move in the downward direction. So there is the suspension of the solids like this, and the gas is moving in the upward direction, and these are the gas bubbles, that is the red color, the bubbles as you see. Then if liquid is in the downward direction and gas in the upward direction, counter flow, but gas is the continuous phase. In 2A, liquid is the continuous phase, inverse three-phase fluidization, and in 2B, gas is the continuous phase, fluidization represented by turbulent contact absorber, TCA. An integrated bed of low density particles are fluidized by the upward flow of gas as the continuous phase. The vigorous movement of the weighted particle give rise to excellent gas liquid contact. So excellent gas liquid contact is possible in turbulent contact absorber. But as far as the use of different types of the modes of fluidization are there, the 1A is the most widely used type, followed by this 2B and 2A. So co-current gas liquid solid fluidized bed, this is generally referred as gas liquid fluidization, because solid, of course solid particles are always there, without that there is no fluidization. So a schematic representation of an experimental setup for three-phase fluidized bed is here. So suppose water is stored in a tank and water is pumped. Water is the liquid phase which is pumped into the vessel which contains solid particles, and water flow or the liquid flow can be measured using rotameters or any other flow measuring devices. For data capture, rotameter is not good enough. Other flow measuring devices, differential pressure cell we can use. Then gas phase is the air used here. So air compressor, the air is entering to the vessel, and the air flow rate is measured again using the rotameter for a laboratory setup. but this can also be measured using other flow meters. And the gas is dispersed to the vessel with one sparger. This is a sparger. So as both liquid and gas moves in the upward direction, impact the drag on the solid particles. So solid particles comes to a state of suspension. And these are the bubbles of the gas. So bed of solid particles expanded up to this, as you see. This is the black dot is the solid particle up to this. That means this is the three-phase region. To that we consider the height of the fluidized bed, three-phase fluidized bed. Above that there is a two-phase region where gas and liquid is present. At the top of the vessel, the gas leaves the liquid, and this part is nothing but the disengagement section, whereas this part is the gas liquid distributor section at the bottom, and the main fluidized bed, which is called as the reactor or the test section, is this much. So bottom there is a distributor section where gas and liquid distributes and mix together and enter to the vessel, and at the top of the bed there is a disengagement section where the gas phase escape the liquid. Then to measure the pressure drop across the bed, pressure drop represents the drag that is required to make the solids suspended. So that can be measured, the pressure drop can be measured using simple differential U-tube manometers, or any other pressure measuring instruments can also be used. So for a simplest setup, the pressure drop can be measured using the manometers. So as you see here, another schematic is here. The bubbles, as you see, so below the bubbles wake is there. Wake means a low pressure region is created below the bubble. That is circulating fluid is there. So liquid and gas, as it enters and moves in the upward direction, liquid is taken out from the system here, and as you see here, liquid is drained, and again it is recirculated. It is going to the tank, and this is the this portion is the gas liquid solid fluidized bed portion, and above there is a two-phase region, gas and liquid. So a photographic view of a gas liquid solid fluidized bed is shown here. Solid particles, as you see, bigger size solid particles for a visual observation that is made. Rashig rings you see that is getting fluidized by the upward movement of the liquid and the gas. And this is hazy, as you see, it is not complete because of a small gas bubble, air bubbles are there in the bed. So it makes the bed hazy. Co-current gas liquid solid fluidized bed, the different types of flow regimes we come across depending upon the flow rate of the liquid and the gas phase. The liquid with the gas forms discrete bubbles which supports the particles. Bubble flow includes liquid supported solids and bubble supported solids. Then liquid supported solids operation characterizes fluidization with liquid velocity beyond the minimum fluidization velocity. So if gas is the continuous phase or the liquid is the continuous phase, depending upon that, the fluidization occurs beyond the minimum fluidization velocity, because about the fluidization already 3 to 4 classes already you have listened, so you know how the fluidization takes place. So a minimum fluidization velocity is there when the liquid is the continuous phase. that minimum fluidization velocity is called the liquid minimum fluidization velocity, and for gas continuous phase it is the gas minimum fluidization velocity. So the different types of flow regimes as we get here, you see in this plot, one is the abscissa, you see the gas velocity, and in the ordinate there is the liquid velocity. So in the low liquid and gas velocity there is the coolest bubble flow regime, and for the low to moderate gas velocity but high liquid velocity, this region it is the dispersed bubble flow regime we get. And for high gas velocity and low liquid velocity we get slug flow regime. In the slug flow regime, with increase in flow rate, the slug frequency increases, that means flow rate of the gas, the slug frequency increases and the volume fraction of the liquid decreases. Then liquid solid mixture forms fragmented agglomerates, eventually operate in mode 1B. That means gas becomes continuous and liquid just trickles down in the trickle flow. So another flow regime classification graphically is shown here. For a high liquid velocity and a low gas velocity. To the left, high liquid velocity, to the right, high gas velocity. And to the left, the gas velocity is low. So when the gas velocity is low and the liquid velocity is high, dispersed bubble flow you get, smaller bubbles are there in the bed, and these smaller bubbles because of high liquid velocity escape fast at a faster rate from the bed. So overall gas hold up in the bed is little less. Whereas if the liquid velocity is high and moderate to high, and gas velocity is little more, then discrete bubble flow we get. Here little larger bubbles we get, little larger bubbles. Here the residence times of the bubbles, because of moderate to high liquid flow rate, the residence time of the bubbles are more, so that the gas hold up in this bed is more. Then the coolest bubble flow, where the liquid velocity is moderate to less and a little moderate gas flow rate is there, so bubble coalescence takes place. That means gas bubbles which are coming from the distributor section coalesce each other and bigger size bubbles are formed, and a wide size distribution of bubbles are seen in this coalesced bubble flow regime. If we further increase the gas flow rate, then slugs are formed. Slug means large gas bubbles are formed, even up to reaching the diameter of the column, and the length of the bubbles even more than that of the diameter of the column. Such things are there. This is the slug flow regime. Another flow regime is the churn flow regime, where it is similar to that of slug flow, but it is a chaotic behavior of the slugs are there. And a frothy type of the bed we get in the form of froth. The gas and the liquid moves in the upward direction. Next, there is a bridging flow regime. Bridging flow regime, you see that liquid forms the bridge. Here it is a bridge. Then another bridge is here. In between there is gas is there, continuous. So this is a bridging flow. Then further increase in the gas velocity, annular flow we get. That means liquid is just in contact with the wall of the vessel, and the gas phase entirely occupies the central region of the bed, annular flow. Then co-current gas liquid solid fluidized bed. The state of gas liquid solid fluidization is strongly dependent on the geometry of the bed, methods of gas liquid injection, and presence of the retaining grid. Retaining grid means it is there to check the motion of the solid, that is retaining grid. So depending upon that, the geometry and you see that tapered fluidized bed is here. So earlier I had shown you in the previous slides, you have seen that cylindrical vessels are there, but here it is tapered conical vessel. Tapered fluidized bed uses a tapered column which diverges at a small angle in the upward direction. And in a spouted bed, the gas and the liquid are introduced into the bed through gas liquid injector. This is gas liquid injector located at the bottom of the bed. The solid particles in the core area are carried out by the fountain and separated from the liquid at the surface of the fountain here. The solid particles then move down in the annular region. So solid moves upward direction like this, then falls like this. Then semi-fluidized bed. A semi-fluidized bed is formed if you arrest the free expansion of the solid particles in the bed by means of a top retaining grid. This is a top retaining grid here. As the liquid and gas velocity is increased through the bed of solid particles, after beyond the minimum fluidization condition, the height of the solids in the bed increases and it may reach at the top of the vessel. And if we put towards the top a retaining grid, so solid particles will form a fixed bed at the top. You see, it is a fixed bed at the top of, or it can be called as a packed bed at the top. So when a mass of fluidized particle is compressed against the porous retaining grid, resulting in the creation of a fluidized bed and a fixed bed in series within a single vessel. At the top you see there is a fixed bed, and below that again the particles are in the form of fluidization. Fluidization means it is the circulation of particles is there. Particles rise to certain extent, then as they lose the momentum fall down again. Because of the drag of the liquid, of flow liquid and gas, again they are lifted to higher position in the bed. So one experimental setup here showing the gas liquid solid fluidized bed. As you see in the transparent vessel, solid particles are there. In the right side figure you see that solid particles are there. Here the figure in the right side shows this the distributor section here, where gas liquid mix up here in this distributor section and enters to the test section, that is the main fluidized bed. This is the test section or main fluidized bed where this fluidization occurs. And at the top you see there is a disengagement section where gas and liquid separates. The gas phase escapes to the atmosphere here in this case, but it can be collected also and taken for some other processing. Similarly, the liquid is drained out and taken to the storage vessel from where the liquid is pumped out. Again, it can be taken for other use for a continuous operation. This is a batch 3-phase fluidized bed setup as far as the solid and the liquid is concerned. Liquid is circulating and the operation is continuous for the gas one. So the gas liquid distributor is like this. It consists of one air spurger. It is antenna type air spurger with small holes on this spazzer gives smaller bubbles, generate smaller gas bubbles here, or the gas jets, which when in contact with the liquid takes the form of bubbles. Then these are the manometers, differential U-tube manometer used for the measurement of the pressure drop, and this is a conductivity probe used to sense the signal of the flow of the gas bubbles. Next, the definition of some three-phase fluidization phenomena. It is classified as a term, symbol, and a significance. The bed pressure drop, usually represented by delta P, it measures the drag in combination with the buoyancy and the phase hold-ups. In three phase, it measures the drag. In two phase, it is only the drag and the buoyancy is of concern. And when it is gas solid fluidized bed in ambient condition, it is the drag is the predominant one, mostly it is drag. But in a liquid solid bed, it is the drag and buoyancy together. But in gas liquid solid system, it is the drag, buoyancy force, and the phase hold up together. Then minimum fluidization velocity, the minimum superficial velocity at which the bed becomes fluidized. That is the minimum fluidization velocity. For the operating conditions, the particles are fluidized primarily by the liquid for a liquid continuous phase. The bed expansion ratio, that means initial static bed height when the particles are not fluidized, which is the fixed bed height. Then with the flow of the gas and liquid, the bed expands, we get a higher height of the fluidized bed. So that height to the initial height, that ratio is known as the bed expansion ratio, measures the extent of fluidization in the bed. So it is the ratio of expanded bed height to the static bed height. Then gas hold up, that means the fraction of the bed occupied by the gas phase, measures the fractional volume occupied by the gas. It is the volume of the gas to the total bed volume. That ratio is the gas hold up. Similarly, liquid hold up is the fractional volume occupied by the liquid, that is volume of the liquid in the bed to the total volume of the bed. Solid hold up measures the fractional volume occupied by the solids. It is the volume of solids by the total bed volume. And the sum of these three phase hold ups, gas, liquid, and the solid, should be equal to 1 because it is the fraction. So the total is 1. Then another one is the porosity. Porosity means the space in the bed which is occupied by the gas and the liquid phases only, which is nothing but 1 minus the volume fraction of the solids in the bed, that is the porosity. Another characteristic is the bubble rise velocity, the actual velocity of bubble as it rises through the bed. And your gas hold up depends upon the bubble rise velocity also. If the bubble rise velocity is very high, residence time of the bubble in the bed will be less and the gas hold up will be less. And for low bubble rise velocity, gas hold up will be more. The qualitative influence of different operating variables. So what are the operating variables? In this gas liquid solid system, the flow rate of the gas, flow rate of the liquid, which is actually represented in terms of superficial velocity of the gas, superficial velocity of the liquid, density of the particles, liquid density, density of the gas phase, surface tension of the liquid, viscosity of the liquid, the particle size, size of the solid particles, the shape factor of the solid particles, phase, and the diameter of the vessel or the column. So few parameters of the bed with which the gas liquid solid hydrodynamics is characterized is nothing but the gas hold-up, bed expansion ratio, bed porosity, and the bubble diameter. With increase in the gas velocity, that means higher gas velocity, your gas phase hold-up increases, bed expansion also increases, porosity increases, because same amount of solids as it is fluidized to a greater height, the solid concentration decreases and the void fraction increases. That means porosity increases. And with increase in gas velocity, your bubble size increases. With increase in the liquid velocity, the gas hold-up slightly decreases because the liquid takes down the bubbles in the bed little faster than at lower liquid velocity. Bed expansion ratio for increase in liquid velocity increases, porosity increases, and a slight decrease in the bubble size is there. As far as particle density is concerned, there is no clear study how the gas hold-up is affected, but bed expansion decreases, porosity decreases. And liquid density, with increase in liquid density, the gas hold-up decreases, bed expansion increases, porosity increases, and bubble size decreases. With increase in the density of the gas phase, no such study by varying the gas phase density is there. And as far as the surface tension is concerned, with increase in surface tension, your the gas hold-up decreases, and your bubble size increases here. With the increase in the viscosity, this viscosity and the surface tension, okay, they come together because you are varying the liquid. So sometimes they club together. So no clear study is there on the effect of the liquid viscosity on gas hold-up, but bed expansion increases, porosity increases. For increase in the particle size, gas hold-up increases, bed expansion decreases, porosity decreases, bubble size decreases, and shape factor has no effect, and no such studies are there. And for the diameter of the column, increase in the diameter of the column, remaining other things same, your gas hold-up decreases, and the studies, no studies are there for the other parameters. Now we will discuss the hydrodynamics of co-current gas liquid solid fluidized bed. So the main parameters are the pressure drop, minimum fluidization velocity, the phase hold-ups, like gas phase hold-up, liquid phase hold-up, solid phase hold-up, your bed expansion, or indirectly it is the directly it is the bed expansion, and the other way indirectly the bed porosity is measured from the bed expansion. So first the pressure drop and minimum fluidization velocity. For a gas liquid solid fluidized system, the minimum liquid fluidization velocity. Liquid fluidization velocity means liquid is the continuous phase. That's why minimum liquid fluidization velocity is the superficial velocity of the liquid at which the bed becomes fluidized for a given superficial gas velocity. Because three phases are there, so gas should be there. So at certain gas velocity, what is the liquid minimum liquid velocity required to make the bed of solid particles fluidized? That is the minimum liquid fluidization velocity. Above the minimum liquid fluidization velocity, there is good contact between the gas, liquid, and solid phases are there. And a bed pressure measurements or visual observations are generally used to measure the minimum liquid fluidization velocity, either from the bed pressure drop measurement, like for the liquid solid and gas solid fluidized bed, the previous classes you have learnt, that is done, or it is by visual observation also, that is done. So a plot of pressure drop through the bed or the pressure gradient, either pressure drop or pressure gradient. Pressure gradient means pressure drop per unit height of the bed. Within the bed versus the superficial liquid velocity displays two linear regions whose intersection corresponds to the minimum liquid fluidization velocity. You can use the visual observation. You can see that as you are increasing the liquid velocity through the bed, initially the bed is stationary, a fixed bed is there. Now the particles will start to move in the upward direction. Okay, that corresponding velocity is the liquid minimum fluidization velocity. That is visual observation, but from the pressure drop measurement also we can have that. So how the pressure drop varies? At zero velocity the pressure drop is zero. As you increase the liquid velocity, the pressure drop will increase because the liquid will impart drag on the solid particles, and the pressure drop is nothing but the representation of the drag force of that the fluid exerts on the solid particles in the bed. So here you see the liquid pressure drop with liquid velocity increases like this. This is one experimental plot, and experimental the velocities are varied in such a way that exact point we are getting here at the minimum fluidization velocity. After that the bed pressure drop remains constant, almost remain constant, or in a gas liquid solid fluidized bed little increase in the this will be there, that bed pressure drop increase will be there, it will not be constant because of the volume fraction of the phases. As the volume fraction of the phases will change, that means phase hold up will change. For that there will be some change in the overall bed pressure drop value, which is not there in the liquid solid bed or gas solid bed, because additional term here is the drag is there, buoyancy is there, and a phase hold up is there, as I have already told. And this is one ideal situation where the beyond the minimum liquid fluidization velocity, the bed pressure drop remains constant. But your experimental observations may be like this. If you are carrying the varying the superficial velocity and bed pressure drop data, here is 1 point like these points are there, and you do not have experiment exactly at the minimum fluidization velocity, but you have the pressure drop values for liquid velocity is higher than the minimum fluidization velocity. So a linear line like this is there, and another horizontal line. The intersection of that here, this is considered as the minimum fluidization velocity. And the bed pressure drop or the bed pressure gradient or pressure gradient in the bed is given by this expression. G is the gravity times of density of the gas phase multiplied by the volume fraction of the gas phase plus density of the liquid phase multiplied by the volume fraction of the liquid phase in the bed plus density of the solid multiplied by the volume fraction of the solid phase in the bed. So that constitutes the pressure gradient in the bed. The variables on which the liquid minimum fluidization velocity of a gas liquid solid fluidized bed depends are gas velocity, this is one operating variable, particle size, particle density, liquid viscosity, liquid density, static bed height, shape of particle, and the gas liquid distributor. Because it is the liquid minimum fluidization velocity is mentioned, that's why the liquid velocity is not written here, whereas the liquid velocity is also a variable. Basically liquid velocity is also a variable, but it is liquid minimum fluidization velocity, so its dependence is written, that's why the other factors are there, because liquid is the continuous phase So it's a minimum fluidization velocity we are going to determine. The following figures, which are there in the next slides, describe the behavior of a liquid minimum fluidization velocity to some of these variables. As you see here, the effect of gas velocity. These lines are for different gas velocities. Gas velocity remain constant. One is 0 gas velocity, that means only the liquid solid fluid bed here. The pressure drop variation is represented by this. And as you increase the gas velocity, your total pressure drop what you measure decreases. For the same amount of solids in the bed, okay, the pressure drop is nothing but the representation of the drag, buoyancy and the phase hold up together. So for liquid solid bed, it was the drag force, it was such high, and as you increase the gas velocity, the overall bed pressure drop as you measure that decreases, and finally for 1 meter per second of the gas velocity, okay, the variation of pressure drop with liquid velocity is like this. As you increase the liquid velocity at a constant gas velocity, your pressure drop increases, whether it is liquid solid fluid bed or it is gas liquid solid fluid bed. Then at the minimum fluidization velocity, beyond the minimum fluidization velocity, the pressure drop becomes constant, almost constant. So as you see here, for liquid solid fluid bed, this is the minimum fluidization velocity. For gas liquid solid fluid bed, for gas velocity of 0.2, this is the minimum fluidization velocity, whereas for the gas velocity of 10 meter per second, this is the minimum fluidization velocity. So as you see, the minimum liquid fluidization velocity decreases with the gas velocity. Higher is the gas velocity, that means gas also contributes for the fluidization of the solid particles, that is suspension of the solid particles. So the amount of liquid that is required to support the solid particles gradually becomes less, so that liquid minimum fluidization velocity decreases. And effect of particle size, higher is the particle, higher is the liquid minimum fluidization velocity. You see that 3 different particle sizes are there: 2.18 millimeter, 3.05 millimeter and 4.05 millimeter. So for 2 point, you see this is the minimum fluidization velocity. For the 3 millimeter one, this is, and for 4 millimeter, okay, this is the minimum fluidization velocity. That means minimum fluidization velocity increases with a particle size. That means the particles are of higher weight, so need higher drag force to get fluidized. And the particle density, lighter particle, coal particle is this, whereas the dolomite is this, having higher particle density. With the particle density, obviously the weight of the particle increases. For the same size of the particle, weight of the particle increases. As the weight of the particle increases, you need higher velocity of the fluid to offer the amount of drag that is necessary to make the particles suspended in the bed. So with particle density, increase in particle density, bed pressure drop increases. Then effect of liquid viscosity. Liquid viscosity, viscous liquid, at low velocity also the drag is more, because it is viscous. Viscosity is more, so drag is more. So that if the liquid viscosity is increased, here in this you see that one is water, 6% glycerol, and the glycerol percentage is varied up to 24%. Highest viscosity is for the 24% glycerol. For water system, you see this is the minimum fluidization velocity here. So it is a exact plot. As you see, beyond the minimum fluidization velocity, slight increase in the bed pressure drop is there. But you see that slope of the curve is different. Up to this is one slope. Beyond that, there is another slope of the line. This is for the increase in the liquid velocity. X-axis you see superficial liquid velocity is there. As you increase the liquid velocity, the bed pressure drop variation is like this. So why it is like this, that we will discuss later. Now you see that with increase in the glycerol percentage, that means a higher viscosity of the fluid, the minimum fluidization velocity decreases. That means less velocity is required to make the bed fluidized. Then effect of initial static bed height. If you just change for the same particle system, okay, different amount of particle if you take, that means bed mass you vary. There is no effect on the minimum fluidization velocity. Minimum fluidization velocity is nothing but the liquid velocity that is needed to make the solid particle suspended. Unless there is variation in the solid density or particle size, simply increase in the bed height does not change the liquid minimum fluidization velocity, whereas what is changed, you see that drastic difference in the overall bed pressure drop is there. For a bed height of 17.7 centimeter, you have the pressure drop, fluidized bed pressure drop, this value, whereas for 26.7 centimeter, you have a fluidized bed pressure drop this, and at 36.7 centimeter, you have this value. Because more amount of solid, so more mass, so higher overall pressure drop is required. But the liquid velocity that is offering drag to a single particle to make it suspended is not changing. So right side this plot shows the variation of a minimum liquid fluidization velocity with gas velocity. So as you see that with increase in gas velocity, the minimum liquid fluidization velocity decreases. Then already about the gas solid fluidized bed and liquid fluidized beds, you know that the experimental observations are correlated to some mathematical equation which are known as the correlations. So correlations are developed for different types of operation in different types of processes, and the correlation for the minimum fluidization velocity are like this. So the liquid minimum fluidization velocity, as we have discussed, it depends upon the gas velocity, particle size, liquid phase viscosity, density of the solid particles, density of the liquid, and your shape factor. So one thing is missing here, which was there, the gas phase density. So for the gas, unless it is a compressed gas, the density of the gas does not change much. As far as the solid to gas, that density difference is there. A solid may be having a density of 1000 minimum kg per cubic meter, whereas the gas air at atmospheric condition, it is having the pressure of 1.2 kg per cubic meter. So any variation little bit, if you take a higher if you take air or if you take carbon dioxide. Carbon dioxide is a little heavier gas, but still it won't be more than 1.4 kg per cubic meter. So large difference is not there. Because of that, the gas phase density is not contributing to this, and the correlation is developed. Using this correlation, if you have different gas velocity, particle size, liquid viscosity, and gas your solid phase density, liquid density, and the shape factor you have, you can determine the liquid minimum fluidization velocity required to make the particles fluidized. The first equation is in the dimensional form, another equation is in the dimensionless form. Dimensional means it is the liquid minimum fluidization velocity, either it is meter per second, centimeter per second, having the dimension and the unit. Whereas it the ratio of a liquid minimum fluidization velocity to the liquid minimum fluidization velocity in the liquid solid system only. No gas is there. In that ratio, it is dimensionless form. Again, another expression is there for that. Then this it can be combined to different types of other dimensionless factors. Instead of the gas velocity, particle size, liquid viscosity and densities of the phases, it can be combined into dimensionless groups. Here this third correlation you see, that is in terms of Morton number, then Archimedes number and gas phase Froude number. This is Froude number, you know. This is Archimedes number and this is Morton number. So this way the correlations are there. For the scale of the system, this type of dimensionless correlations are good. But for the calculation of the liquid minimum fluidization or any other parameter, such correlations are easier to have the calculation on that. Next hydrodynamic parameter is the solid hold up and bed porosity. So as bed porosity we have discussed. In the left hand side one photograph is here. You see that it is almost a fixed bed it is. Little bit fluidization is there, almost a fixed bed. So as you increase the liquid and gas velocity, your bed get fluidized, solid particles are suspended. Now height of the bed is this. So height of the bed increased. So this is nothing but known as the expanded bed height. This is the expanded bed height, HE we can write. And this is HS, static bed height. So the ratio of HE to HS is nothing but the bed expansion ratio. As the bed expanded, so the void space between the, because in the packing we call as the void space, it is not the void space but the free space in between the solids, that you consider as the bed porosity. So bed porosity increases with the expansion of the bed porosity increases. So bed porosity is a parameter which is used for the calculation of many things. That's why it is in the form of a bed porosity, but usually for any experimental observation or anything for the sizing of the system, it is not the bed porosity, rather the expanded bed height is of importance. So what should be the height of a fluidized bed? Depending upon the porosity you need, your expanded bed height will be there. And once you have the expanded bed height, the highest expanded possible bed height is there. From that you will design your system, that height of the fluidized bed you will design. Otherwise what will happen? Particles will come out from the vessel. Suppose it is the vessel top. Now it is fluidized up to this. If I further increase the liquid velocity here, then what will happen? The particle will further expand and the particles will come out from the bed. So sizing of the system, the height is one parameter, diameter is another parameter. The solid hold up in the bed is expressed by this. This is the mass of the solid upon the density of the solid. This is the column area of the column, cross-sectional area of the column, and it is the expanded bed height. So cross-sectional area of the column multiplied by the expanded bed height, that is the total void volume. Mass of solid to density of the solid, this is nothing but the volume of the solid. So which is nothing but the volume of the solid to the volume of the bed, it is basically. That is nothing but the solid fraction, solid hold. And bed porosity is nothing but 1 minus the solid hold up, which is the sum of the gas hold up and the liquid hold up. From the knowledge of solid mass and the expanded bed height, the bed porosity can be calculated. So usually any experimental finding is represented in terms of expanded bed height or bed expansion ratio, which is again converted to bed porosity. The expanded bed height is generally observed visually if particles are little large in size. That means visually you can see the particles inside the bed, and if the vessel is a transparent one, or from pressure gradient measurement along the length of the column, or by sensing the signal from conducting probe or optical probe. So any conducting or optical probe, if I keep in the bed, suppose this position one probe is, this position one probe is, this position another probe is there. If solid will reach this signal from this probe I will get a different signal. If the solid particle will reach here, then this probe will give the signal. Similarly, the other probes they will give the signal. Using that we can have, or otherwise the pressure gradient. Pressure gradient means the total pressure drop upon the height of the head. So if you have the pressure ports at different locations you may have the pressure port. Using those pressure port, if you measure the pressure drop, also the expanded bed height can be known. Like if the solid particles below this probe, okay, your pressure gradient will be something. For gas liquid phase only, above that, okay, one pressure drop will be there. And once the solid particles will reach this here, this point, and it will be above that. So the amount of solid particles, they are just above this port, will give a different pressure drop value. So pressure gradient along the bed will be different. From that also, the expanded bed height can be measured in a opaque system. The following are some typical bed expansion behavior of a three-phase fluidized bed experimentally observed. You see in this plot, this is a bed expansion ratio in the ordinate, and in the x-axis there is superficial liquid velocity, and the legend shows that different gas velocities are there. So these lines represent different gas velocities and the variation of bed expansion ratio with liquid velocity. As you see, with the increase in the gas velocity, the bed expansion increases. For the same liquid velocity you see, this is the liquid velocity. So at 0.08 meter per second of the liquid velocity, for a liquid solid bed, without the absence of gas, this is the height of the bed you can say, or it is the bed expansion ratio. But as you increase the liquid velocity, increase the gas velocity is increasing, so you see the bed expansion ratio is more. That means height of the expanded bed is more. So bed expansion ratio increases with the liquid velocity and with the gas velocity. Next is the plot of the bed expansion ratio with the particle size. Higher is the particle size, less is the bed expansion ratio. Here you see larger size particle, this is the bed expansion ratio variation with the liquid velocity. Smaller is the particle, to a more height it is getting fluidized. Expanded bed height is more and bed expansion is more. Particle density has a significant role on the bed expansion ratio. With increase in particle density, the bed expansion ratio is less. For coal, the bed expansion ratio is the highest, then followed by this dolomite having dense specific gravity in the range of 2.6 to 2.8. Coal is having 1.5 to 1.6. Iron, this is iron ore. Hematite, it is in the range of 3.8 to 4.2, whereas this is laterite, it is close to 5 specific gravity. So as with this, your bed expansion with increase in the particle density decreases. Then liquid phase viscosity, more is the viscosity of the liquid, more should be the expansion. 6% glycerol, you see this 6% glycerol is this, whereas 24% glycerol is this. So more is the viscosity, more is the bed expansion. Little bit bed expansion is more. But this is one experimental finding which was earlier that was not available, because the qualitative influence of different variables, as I had discussed in the table, this thing was missing. bed expansion ratio, effect of initial static bed height. Initial static bed height has no effect on the bed expansion ratio because it is the expanded bed height to static bed height ratio we are measuring. But more is the amount of solids, to a more height it will go, but the ratio is almost constant if you see. So then the bed voidage is calculated from this bed expansion ratio, and this plot shows the bed voidage calculated here from different types of correlation. It is calculated, and experimentally also it is calculated at different gas velocities and liquid velocities, and at different gas and liquid velocities the variation of the bed voidage is represented by this, because the bed expansion ratio varies with gas and liquid velocity, which already you have seen. Accordingly, the bed voidage also varies. The bed porosity has been found to be a strong function of the liquid velocity and gas velocity, particle density and particle size, but comparatively a weak function of the liquid viscosity, static bed height and a size of the column. So few things are shown here. With you see that liquid density, not much effect there. Liquid viscosity also not much effect is there. Again, correlations are developed for bed porosity in dimensional form, different dimensional form. This is the different correlations for the bed voidage. This bed voidage epsilon is nothing but the sum of the volume fraction of the gas and a volume fraction of the liquid in the bed, and this is the void fraction or the bed porosity for the liquid solid bed only, no gas is there. For that the relation is like this, whereas because the gas velocity term is missing here, as you see in this relation. For other correlations, that is the gas velocity term is there. One is this is the bed porosity, this is the bed expansion ratio. Similarly, for the liquid solid system, the bed expansion ratio is this. And in dimensionless form, whether it is the bed porosity or the bed expansion ratio, in the form of a ratio of this to that of the liquid solid system is represented. So the bed expansion ratio of the gas liquid solid fluidized bed to the liquid solid fluidized bed is expressed by this correlation, whereas the bed voidage for the gas liquid solid system to the liquid solid one is given by this relation. So these correlations can be used for the calculation of the bed porosity if you know the situation of the operating conditions. Then the other hydrodynamics parameters are the bed pressure drop and a phase hold up. Equations used to determine the volume fraction of each phase in a three-phase fluidized bed are: one is the sum of the volume fraction of gas, liquid and solid phases equal to 1. Then the pressure gradient relation, this is delta P upon delta H, which is G times of rho G epsilon G plus rho L epsilon L plus rho S epsilon S. And the solid fraction, solid can be measured easily, amount of solid in the bed, and if you have information of the amount of the solid in the bed, that is the mass of the solid, then you can determine the solid fraction. Other promising methods for measuring the local gas hold-up are electroresistivity and electroconductivity methods, that is gamma ray transmission measurement and a radioactive tracer technique. Some of the techniques are invasive in nature, and some of the techniques are non-invasive. So what is invasive? If you are inserting a conductivity probe, then it is disturbing the situation of the things in the bed, and if you are not inserting any foreign substance, using gamma ray radioactive tracer, we can scan the bed so that it is a non-invasive technique it will be. So here in one experimental setup, this is a conductive probe is shown. The Either it is a single probe or it is a dual probe. Dual probe means one suppose bubble is moving, it is touching this probe, it will have one signal, another it is touching this, then it will have another signal. Then through this the bubble rise velocity can be measured. Suppose first signal at some time for this probe we get, then for the same bubble another signal we will get from the other probe. So that how much time difference is there, from that the bubble rise velocity can be determined. Also the size of the bubble can be determined. If it is touching this probe and this probe together, we will have a one kind of signal. If it is touching only one probe, not touching the other probe, that means the bubble size is smaller than the distance between the two probes, so size cannot be measured. But for a single probe, only when the gas is touching the probe, you will get a different signal, and the signal transmission using this type of arrangement can be done. So as you see, the signal is captured here. When in the absence of the gas bubbles, this is the line that is representing, that is for the liquid in the system. This is the signal, and when the gas bubble is touching that, depending upon the size of the gas bubble, you have a signal like this, down signal you are getting. And these are the different points. Such a way, if you take the signal and average it over the entire bed, then average bed gas hold up in the bed you will be able to determine. Another more direct method is a phase isolation method, in which we simply isolate a representative portion of the test station by simultaneously shutting down two quick closing valves. Through in the liquid line and the gas line, if we install quick closing valves, suddenly that can be closed, so that the flow of the liquid and the gas to the bed will stop completely. As it will stop, the gas will escape the bed, only liquid and solid will be there. That means the bed height, the overall that two phases, liquid and solid bed height, or it is the liquid height in the bed will be something. So from that this can be measured. So say suppose it is the height of the expanded bed. Now with the escape of the gas, this is H, and with the escape of the gas, only the liquid solid, the height is this is HL. This can be easily measured, and the hold up can be calculated from that using this relation, H minus HL upon H times of 100. This is nothing but the gas hold up in percentage, but fractional gas hold up no 100 is required. So gas hold up variation with gas velocity, liquid velocity is like this. So the effect of this is for different gas velocities. Variation of liquid velocity is there. So with the liquid velocity at different gas velocities, the gas hold up decreases slightly. It is not a strong function of the liquid velocity, whereas here with the variation of the gas velocity, the gas hold up increases significantly. But with liquid velocity, at different liquid velocities, these values. So for this gas velocity, if the liquid velocity is different, no drastic change in the gas hold up is there. So for different viscosity of the liquid and the liquid density, it is basically not the density of the liquid, rather the liquid viscosity. So liquid viscosity is there, and with these different liquids, your surface tension is also different. So combined effect is there on the gas hold up. As you see, for the water system, this is the gas hold up variation with the liquid superficial velocity, whereas for 24% glycerol solution, this is the value. That means gas hold up is more for higher viscous solution than that of the low viscosity liquid. The gas hold of variation with the liquid velocity to gas velocity ratio. Liquid velocity to gas velocity ratio, you can see that two different regimes are there. One regime is this up to one kind of slope, another is this kind of slope. So if liquid velocity predominates, you have the gas hold of values, less gas hold of values, and when gas velocity predominates, you have higher gas velocity, gas hold of values. Similarly, your liquid velocity, with increase in the liquid velocity, your liquid phase hold up increases because more liquid is there in the bed. That is as per the inventory. So liquid hold up increases, and with gas velocity, liquid hold up decreases slightly. So correlations are developed for gas hold up. The gas hold up correlation in dimensionless form and dimensional form are available here. In dimensionless form, it is the Morton number, Eötvös number, liquid phase flow number. This is the ratio of diameter of the particle to the diameter of the bed. This ratio, these are in HR means height ratio, then gas phase flow number and the particle shape. So many factors are correlated. They have the gas hold up value depends upon these variables which are combined to dimensionless units. Okay, let me finish this class here. Another computational hydrodynamic study of this gas liquid solid fluidized bed, little bit I will discuss in the next class. Thank you all.